And finally, for the third question, we are asked to calculate these parameters. Here we have a small distribution system, and the lines are assumed to be lossless. And at the beginning, it is assumed that the capacitor is not connected. For the first part, we have to assume that load 1 is connected in Y connection. So it's asking for phase voltage and current of the first load. First of all, always we have to be careful that the question is asking about phase voltage or line voltage. In this case, it is phase voltage. So when we're going to calculate the voltage here, and we only have the voltage at this bus, we have to, for example, write, if we name this one V1, V1 would be this voltage, let's say V0 minus the impedance between those lines multiplied by the current. But here, since it is assumed that the lines are lossless, so the impedance is 0. So the voltage of all of these buses are 480 volts. But this voltage is the line voltage, and in the question we are asked to calculate the phase voltage. So we have to divide this 480 by the square root of 3, which gives us 277 volts for the phase voltage of this bus, or actually all of these buses. After that, we are asked to calculate the current for this one. For current, we know that the active power is 100 kilowatt and the power factor is given to be 0.7 lagging. So we can use the formula that we were using in the previous questions, S equal to 3 multiplied by phase voltage and phase current. But another approach which is more straightforward is using this formula, which gives us active power directly based on phase voltage, current, and power factor. So knowing this formula, everything is easy. We have V, we have active power and power factor. So easily we can calculate I. The current is calculated here. We wanted phase current. But be careful that this load is Y connected. So we know that in Y connection, line current and phase current has the same value. So this is both phase and line current. So we don't need to change anything. In part B, we are asked to determine the reactive and apparent power consumed by the load 1. We have active power, and we know that S is actually it's better to write P is S multiplied by PF. So in this case we can say S is P divided by PF. We have P, which is 100, and PF is 0.7. So we have apparent power, and Q is root square of S square minus P square. It is one approach, and another approach is using this formula, because we have already knew the active power. We can use this formula to obtain the reactive power, and then based on this formula calculate the apparent power. Based on both approaches we can obtain the same values. And finally, not finally, for the next part. Part C asks for the real and reactive power consumed by load 2. Again, we have some of the parameters and we are asked for the rest. In the previous case, it was active power and power factor. In this case, it is apparent power and power factor. So for active power, we can obtain the P by AT multiplied by 0.8, which gives us 64 kW, and the reactive power would be apparent power, uh, actually root square of apparent power square, which is AT, sorry, minus 64 square, which gives us 48 as we have here. For part D, we have to determine the apparent power supplied. As the lines are lossless, we know that the power supplied by the source is the summation of the powers consumed by these two loads. So we can write that P total, for example, is P1 plus P2, and Q total is Q1 plus Q2. It gives us 102, and this is 184.02. Am I right? Oh, that is 140. Sorry, it's 160. One six six, and these two. Where is Q2? This one and this one. Oh, I made a mistake here. P1 is 100 and P2 is 64. Q1 is 102.02 plus Q2 48. Now it is 164 and this one is 150.0.2. And clearly S total is root square of P total square plus Q total square, which gives us 222.26 kilovolt ampere. Also, you can use this method. Both will lead to the same result. For the next part, part E, determine the power factor at the 480 volt bus. Well, we know that the power at this bus is the values that we already have calculated here, and for calculating the power factor we can just write P total divided by S total, which will be 164 divided by 222.26, which gives here 0.74. And for the last part, again, like the last part of the question 2, we need the system to have 0.9 power factor, and for this sake we have to connect a capacitor here. The power factor was 0.74, so we have to inject some reactive power to increase the power factor. For this case, we had 150 kilovolt ampere reactive power from the source to supply these loads, and in this case the power factor was 0.74, but now we want the power factor to be 0.9. So for this case we can change active power, so active power is the same as 164, but we can change S. I just call it S new. So we can find S new as 164 divided by 0.9, which gives us 182 kilovolt ampere, and clearly new reactive power is S new square, actually root square of S new square minus P square, which is actually P total, and it would be 182 square minus 164 square, which gives, also we have the value here, 79.4, and we are not asked to calculate the capacitor value, so we just need to determine the capacity of the capacitor. So QC is the difference between the new reactive power and the one that we had here. So in this case we can just write 150.0.2 minus this new value 79.4, which gives us this 70.59. And if we wanted to calculate C, we could use the approach that we used for the last part of question 2.